Hello, everyone. Is this? Yep. Okay. So my name is Khurram. This is Abhishek. We are both a PhD student at the University of Alberta, and we work on reinforcement learning. More specifically, we work on algorithms that can learn very quickly, so in minutes or seconds as opposed to hours, from an online stream of data. So while you're interacting with them. And when we saw this hackathon, we thought about, well, maybe we could try our algorithms on the EEG data stream and see how well they work. So this is what we're going to present right now. So one problem that is very common in EEG data is this problem of high interpersonal variability, which is that if two different peoples look at the same thing, then the EEG signal generated from their brain is very different. So for example, this is me clenching my jaw, and this signal was measured by a mu sensor, and you can see this is how the signal looked. And then I did it again, and this is the second signal. Now Abhishek, my partner, he did the same thing, and the signal looked drastically different for his case. So if you were to train a single model that would work for every single human, then clearly your model cannot rely on signals that are not common among humans. So it has to rely on the intersection of the common things, which are not that many. And so this is one of the reasons why we see that large models trained on multiple people do not have very high accuracy. So an alternative is that we can train models that are specialized to humans. Now this is not very easy because what would be the naive way of doing it? We could train a model on the data of every single human, so we can get a data set, label it, train the model, deploy it. That's not very practical. That also has a lot of privacy concerns. So we're going to do something different, which is we're going to learn the model online when we are never going to store any data when we learn the model. So now Abhishek is going to demonstrate how we would do it.
Okay, so that's me. And what I'm going to do is, so this is the real-time EEG signals that you see up on the screen. And they are in the frequency domain. So it's like a Fourier transform of the actual raw data. And it's for two channels, which are located on my forehead somewhere here, left and right. And so if I, let's say, clench my jaw, which you saw a screenshot of earlier, you'll see something there, right? So something very little, something jittery. But now let me do something which is more on like one side versus the other. So let's say like raising my eyebrow. Okay, now look at it again. So I'm raising my eyebrows alternately. Okay, so that's the data stream. And then we are going to train a neural network right now as we speak and try to control this sort of dog to go left and right. So for the demo, and if the dog does the right thing, we are going to give it a reward, just like how you would train your puppy. If it does the wrong thing, then you say, okay, negative reward, -1, right? So the red curve that you see on the left, that's the reward. So this is like a positive reward, which goes up, a negative reward, which goes down. Okay, so now let's get to the demo. Okay, so here's the puppy. Okay, and what I'm going to do is I'm going to raise my right eyebrow to make it go right. If it does that, I'll give it a positive reward. If it doesn't do it, I give it a negative reward. Okay, so let's start. Didn't do it, so negative reward. Still didn't do it, negative reward. Okay, positive reward. Good. Good boy. Okay, so now I think it's sufficiently trained, so I'll leave it, and now I will just okay. Good boy. Okay, so now this is, as you saw, I trained it with maybe 30 seconds of data, and now it is sort of reliably doing what I want it to. And now I'm going to show you a model with 5 minutes of data where we trained it to go left and right. And again, I will leave this here. And okay, so let's make it go clockwise now. And the other direction. And again the other one. Okay, and so now how it is done is what Khurram will tell you.
Yeah. So this is like all running real time, and this is all learning on this laptop on a single CPU. So normally that's not how machine learning models are trained. You need large GPUs, a lot of data and stuff. So the reason it's possible is because this is a new class of neural networks that we at UFA have been working on for a while, for many years. They are event driven, so they only do computation when they see something and they learn in real time. And they're all implemented from scratch in C++, so very efficient implementation. And then the focus for these algorithms are that we want to be able to learn from few samples, not from hundreds and thousands of samples, and we want to learn from few resources, so we should be able to deploy it on an embedded system. So I have tested this model on a Jetson Nano, and it works perfectly fine, and can learn from image data or similar EEG data. Now, there are more details in our papers if you're interested in reading the more details. So some of the work is not published. It will probably be out in a few months, but some of it is published. There are some conclusions. Why should we care about this? This is just we're controlling a puppy with our muscle twitches. Well, that's just a demonstration. Clear. There are other usefulness of the system. For example, if our system can learn to associate any action with any muscle twitch or any gesture, then it has significant implication for improving accessibility. So for example, you can imagine being able to control your cursor with your muscle twitches or your mind if you're not able to use your with a mouse. And right now we're using a Muse sensor, which is very limited. So if you had a better sensor and you trained it for much longer, not for 5 minutes or not for 30 seconds, then you could do more complex things. So you could, for example, in principle, train it to take actions by just thinking about something. So for example, control the cursor by thinking about making it to move in a direction, and turning on a light by thinking about it. Because the learning is happening on device, which means there are no privacy concerns. We don't store data, and it's also very easy to deploy. We just ship the algorithm, and that's it. And that's it. If you have questions, we would love to answer them.
Okay, I can start. What would be, this is a very cool technology indeed. I liked it. My question is, who will you sell it to? Who is going to want to buy it?
So that's a really good question. There are two potential avenues that we see. One is that we can just say we're going to improve this product a bit more, make a more impressive demo, and then we can get some funding to make products which we can sell to, again, people with disabilities, who cannot maybe use a mouse cursors, if they can use any gestures, any muscle twitch to control anything that can have huge implication. Then the other option is we can talk to companies that are already working on making this system. So for example, in our university, there is a prof, Patrick Pilarski. Their labs is focused on developing algorithms so that people who amputees can learn to control cybernetic arms. So there is already a market which is trying to solve this research problem, and we could either sell it to them or we could try to make our own thing. But this is not something that we have decided yet.
Just a suggestion, find your problem and then train it to make it better, rather than going the other way around.
Thank you. Thank you.